we're going to do 3 examples that illustrate problems that you might see in which the mean value theorem is really useful. So in the first example here, we have suppose that f of 2 is equal to negative 3 and f prime of x is less than or equal to 1 on the interval 2, 5, which is a closed interval. The question is how large can f of 5 be? Okay, so this question is basically telling you where the function starts. Okay, it starts at this, we have a starting point on this interval, and it tells you a bound on the growth of the function. So this is basically saying the rate of growth is bounded by 1. So the question is, how much can this function grow? What is the most the function can grow? So like, how large can f of 5 be? With these questions, I usually start off by drawing just like a quick sketch of, just kind of playing around with the different values. Okay, so in this case, we have f of 2 is equal to 3. So like I said, this is where the point, where the function starts. So it starts at this point, or at least where on this line interval, okay? And then the question is if we know that the growth is bounded by 1 or the derivative is less than or equal to 1, how large can this function be? So for instance, let me just draw a line for, so for instance, could my function go all the way up here? Is that possible? Or is the function, bounded by some value, okay, because of this condition? So sometimes what I like to do is I like to think of the most simple possible type of function, and that would be a line. So let's suppose, just to kind of get a sense of what's going on, let's suppose f of x was just a line with slope 1. If f was a line with slope 1, then f would have to look something like this, right? And in that case, 5, f of 5 would be 6. Now, if that was true, that f was a line and f prime of x was equal to 1, that is the largest that the derivative could be. So this is an example giving you the absolute largest that the derivative could be. And so this should give us some intuition that it seems like the answer is 6, just based on this kind of guessing and looking at lines. But of course, we don't know that our function is a line. So we're going to use the mean value theorem to actually prove this for any function f that satisfies these two conditions, okay? So let's start there to actually answer this question. Okay, so the first thing I'm going to point out is that if f prime of x, if we were told that f prime of x is less than or equal to 1, then we actually know that f prime of x exists on the interval 2, 5. So the function is differentiable. In particular, it's differentiable on the interval 2, 5. We also know that because it's differentiable on this interval, we also know that the function is continuous. Because differentiability implies continuity. So this implies the hypotheses of the mean value theorem are satisfied. And what that means is that the conclusion holds. There must be some value c in the interval 2, 5 such that f prime of c is equal to f of 5 minus f of 2 over 5 minus 2. There has to be at least one value c in here, okay, such that the derivative at that value of c is equal to this quotient. So I've plugged in everything that I know. Okay, the next thing that I'm going to do is I'm going to, since the original question was about f of 5, like how big can f of 5 be, I'm just going to solve for f of 5. So I'm going to say f of 5, so 3 times f prime of c is equal to f of 5 minus 3. And now I'm going to add 3 to both sides. So I have 3 times f prime of c plus 3 is equal to f of 5. So I don't know what f of 5 is. We don't know, it was never given. And we don't know what c is. But we do know something about f prime of c. Okay, going back to the statement of the question, we know that f prime of c is less than or equal to 1 on this interval. The derivative is less than or equal to 1. So f prime of c has to also be less than or equal to 1. So how can we use that? So if I go back down here, I know that this quantity here is less than or equal to 1. Okay, the growth of the function is bounded by 1. The derivative is less than or equal to 1. But that allows me to say that this quantity here has to be less than or equal to 3 times 1 plus 3, which is equal to 6. Okay, so I'm just using the inequality because this guy has to be less than or equal to 1. So that allows me to write this inequality here and say, well, then this whole thing has to be less than or equal to this quantity here, which is 6. So there you have it. Our final answer is, we're proving it for any type of function f, not just a line, is that f of 5 has to be less than or equal to 6. And that is happening because the growth of our function, the derivative, is bounded by 1. So let's do a second example, very similar to the example that we just did. In this example, the question is, does there exist a function satisfying the following? So f of negative 1 is equal to negative 2. F prime of x, so the derivative or the growth rate of the function is always greater than or equal to 2. So this means the function has to grow by 2 units. I mean, so for every unit I move right, roughly speaking, I've got to move 2 units up. Okay, so this is pushing the growth to be faster. So is it possible that I can have a function that satisfies these two conditions and yet f of 1 is equal to 0? I always start by thinking about this as like kind of the growth rate, or it's the derivative, the slopes of the tangent lines have to be at least 2. And this is kind of like my starting point, right? And I always start by thinking about my starting point, my growth rate, and kind of this is like where I'm going to end up. And then I always start by drawing kind of like a little bit of a picture. My starting point here is f of negative 1 is negative 2, so it's over here. And my function on average is, the derivative is greater than or equal to 2. So I kind of think about the growth rate. It's got to be, growing by, slopes of the tangent line will be at least 2. So, and if I think about, this point over here, and let me just make that a different color. This is f of 1 equals 0. So this point is over here. So the question is, could I have a function whose derivative is always greater than or equal to 2, and the function goes from here to here? We don't know exactly what it looks like, but is that possible if the growth rate is, or if the derivative is greater than or equal to 2? So what I'm going to do is then I usually think of the case of a line. So let's suppose, just because that's the simplest case, so let's suppose I had a line, and let's suppose the slope of the line was equal to 2. So I started at this point, and then for every unit I move to the right, if my line had slope 2, it would go through here and here. So this is what a line with slope 2 would look like, and this is actually the smallest the derivative could possibly be. This would be f prime of x is equal to 2 for all x, okay? That would be an example, and that's a line with slope 2, and you can see it does not work out. That line could not, is growing, the growth is pushed to be too fast so that it could never go through this line, this point over here. So I'm not very optimistic when I look at the easy case with a line. And my guess would be that the answer is no. But again, our function f is not a line. You know, it could be many different things. So what I'm going to do is I'm going to use the mean value theorem to take a look at the situation for all functions. So in this case, we are told once again, the derivative is greater than or equal to 2 on this for all x, right? So that implies if f prime of x is greater than or equal to 2 for all x, then I know that the derivative exists on all real numbers, right? And in particular, f is differentiable on the interval -1 to, let's use -1, 1. I also know that f is continuous. It's continuous for all x, so it's continuous on the closed interval, -1, 1. So right here we have mean value theorem is satisfied. The hypotheses are satisfied. And what this implies is that there must exist some value c that is in the interval -1, 1, such that f prime of c is equal to f of 1 minus f of -1 over 1 minus -1. So f of 1, so we have 0, a minus, so let's suppose that there was such a function. So we would need f of 1 to be 0. F of -1 we said was -2. And here we have 1 plus 1, so that's 2. So in this case, if there is such a function, then there has to be some value c in this interval here, okay, in this interval, such that the derivative is equal to 1. Okay, but in this case, that's not possible. If f prime of x is always greater than or equal to 2. So no such function exists. And just to recap, the reason, right, is that we just showed that if this function is truly differentiable on -1, 1, and it's continuous on -1, 1, the closed interval, okay, then there has to be some point, some c value in here such that the derivative is equal to the slope of the tangent, or is equal to the slope of the secant line, but the slope of the secant line is 1. And if the derivative always has to be greater than or equal to 2, then this guy can never be equal to 1 because this guy is greater than or equal to 2. Okay, so we have it's not possible, there's no such function. For this example, suppose our derivative is bounded above and below, so the derivative is less than or equal to 3, but it's greater than or equal to 1. So the function is growing, but it's limited in how much it can grow here, and it must grow at least by 1, and that's true for all x. We want to show that the change in the function over the interval 2, 5 is less than or equal to 9, and it is greater than or equal to 3. So again, we're going to use the fact that since we are told the derivative is defined for all x, right? So f is differentiable for all x, for all real numbers. But in particular, I'm going to be looking at the 2 and the 5. Because I see that would conveniently fit with my mean value theorem. So f is differentiable on 2, 5. And this also implies, the fact that f is differentiable on all real numbers x also implies f is continuous on the interval 2, 5. So this implies closed interval. So this implies the mean value theorem applies. Okay, and there must be some value c. So there exists c in the interval 2, 5, such that f prime of c is equal to f of 5 minus f of 2 over 2 minus, or over 5 minus 2. Okay, so basically this is telling me there exists a c such that f prime of c, so the derivative, is equal to f of 5 minus f of 2, and this, the bottom is just equal to 3. And I'm going to, since we're being asked for a question about the difference, so I think of this as like the growth in the function. Or in other words, it's like the change in the function as we move from x equal 2 to x equal 5. How much does this function increase or decrease? It's like the delta y, the change in f. So that's really what we're looking at. So I'm going to keep these together. I'm not going to solve for this guy or solve for this guy, because my question is about this difference, the growth in my function, the change in my function value. So instead, I'm just going to solve for it. And I have that 3 times f prime of c is equal to f of 5 minus f of 2 for some derivative. Okay. Now I go back and I look at these bounds. I know that this guy has to be at least equal to, is greater than or equal to 1. And I also know that this guy is less than or equal to 3. So that allows me to write the following inequality. F of 5 minus f of 2, which we know is equal to 3 times f prime of c for some derivative. We know that this has to be greater than or equal to 3 times 1, okay, because this guy, the derivative, has to be greater than or equal to 1. We also know the derivative has to be less than or equal to 3, and therefore we can write this inequality. F prime is less than or equal to 3, so this has to be less than or equal to 3. Okay, and then these are the connections I'm seeing here. F prime of c has to be greater than or equal to 1, and it's less than or equal to 3. So my final answer would be that 3 is less than or equal to f of 5 minus f of 2, which is less than or equal to 9. And then that solves, that's my final step.